It turns out that calculating determinants is a difficult task. For the small matrices, 2 by 2, 3 by 3, it's not too bad, but as soon as you get bigger than that, there just becomes a lot of calculations, and we need to find a simpler algorithm for solving it. And it turns out that as we look for that simpler way, we'll actually run into a lot of interesting results that are going to let us calculate some determinants really quickly. So it turns out that row operations can be used to to calculate matrices. Let's take a look at how some of this works here. So I'm going to start off here with just the theorem, let A be a square matrix. If A has a row or a column of all zeros, then the determinant of A is equal to 0. And that's pretty easy to see because that row or column, just choose that row to be the one you expand around. Right? So for instance here, I've got this one, and the determinant would look like, I'm going to expand across the first row here. 0 times some minor, or cofactor, I guess, minus 0 times another subdeterminant plus 0 times another subdeterminant. I'm putting question marks in there, not that I don't know what goes in there, but just that I don't care because I'm multiplying by 0. The whole result's going to be 0, right? Now, this result here, I think we talked about in class, that the determinant of A transpose is the determinant of A. And we can see this by just when you look at how do you find the determinant of A. You're going to do expansion across some row or column. Well, then when you calculate determinant of A transpose, if you use the ith row here, then use the ith column there. That the calculations will look exactly the same. Whatever you do here, whatever row or column you use here, use the same column or row there. And even on the subdeterminants, as you look at a subdeterminant of this one thing, calculating the minors, if you use a row to calculate a minor, then you're going to use the corresponding column to calculate the minor over on this side. And the calculations will be identical. And you get the same result. This being said, a lot of the stuff that we're going to do with row operations or looking at rows can be just completely analogous to saying, well, look at columns instead, because anything we do with rows, you can then say, well, just do it to the transpose, and you're talking about columns, and the determinant of A and determinant of A transpose are the same. So anyway, we're going to work with row operations, but similar things can be done with column operations. So here we go. Next, theorem. Let A be an n by n matrix. All right, so this is looking at what the effect of row operations has on the determinant. So if B is a matrix that results when a single row or column of A is multiplied by a scalar k, then the determinant of B is k times the determinant of A. The proof of this is actually in the textbook, so I will not give it here. The thing is, if you multiply just a single row of A by a scalar k, then the determinant gets multiplied by that same scalar k. I think in class we looked at if you multiplied the whole matrix by k, that it didn't work, but just multiplying by one row does that. 2, or B here, if B is a matrix that results when two rows or columns of A are swapped, then the determinant of B is minus the determinant of A. And the last part is, of course, there's one more elementary matrix, one more elementary row operation, so the result of that. If B is a matrix that results when a multiple of one row or column of A is added to another row or column of A, then the determinant of B equals the determinant of A. This to me is crazy. It seems like there should be some effect on the determinant because it seems like such a big, the other two row operations are pretty simple. This is the most complicated of the row operations, and yet it does not change the determinant. Let's see why. I'm going to prove just this last one. The book proves part A. I'm going to prove part B. Sorry, part C. I'll leave part B to you to prove. So here we go. So I'm going to look at a matrix just for the sake of argument. I'm going to say I take the ith row of matrix A, multiply it by K, and add that to the first row. So it's the first row I'm focusing on. So when I take the determinant of this thing, I'm going to do it by expanding across the first row here, the one that got added to, in my case, the first one. So I've got the first entry here times cofactor 1, 1, and then the second entry times the cofactor 1, 2, and so on down the line. So this is in this position times cofactor 1n. Now I'm going to use the distributive property. This is all just numbers at this point. I'll multiply these cofactors in, distribute them in. So in particular, I've got A11 times C11, and A12 times C12, and A13 times C13, all the way up to A1n and C1n. I'm grouping those all together here to start with. Then a bunch of these have k's in it. This is k times these two things, k times those two things, and so on. So I'm going to factor that k out right here and see what I have. So I've got AI1 C11 and AI2, this should be a 2 right here, AI2 C12 all the way up to AIN CIN C1n. That's a 1 right there. Huh. Wonder how many more mistakes I'm going to find. Probably a lot. Okay, so A1n, sorry, AIN C1n. I notice that this stuff right here in parentheses is the determinant of A. Now I have plus k times all this stuff. And in order for this theorem to be true, I need to make the argument that the stuff in here adds up to 0. So that we end up with this just equaling the determinant of A. So how do I argue that this adds up to be 0? Now, what I do is I come over here and I say, consider the following determinant. So here's a matrix that is not quite matrix A. All of it's matrix A, except what I've done is I've just replaced the first row to be exactly the same as the ith row. Because I claim that's what this, that's what this looks like. When I take this determinant, this determinant, it looks like this. So I'm expanding across the first row, but the first row is now the same as the ith row. So I have AI11 times this cofactor, and then AI2 times the cofactor that's got, this column and then the rest of this stuff, and so on across. So the cofactors here are the same as they would be for matrix A expanding across the first row, but now I just have a different first row. All the other rows are the same, so all of these cofactors are the same as what they would be for A, but the things I'm multiplying by are different. Okay. What's happening here, when I look at the final result of all the elementary, what did I call them? The elementary products. So you take something from the first row, something from the second row, something from the third row, making sure you never pick two things from the same column. And you look at all the possibilities, right? There's going to be, for instance, there's going to be one possibility that's got this right here. It's going to have the AI1 from this first row, and it's going to have the AI2 from the ith row, and then it's going to have more stuff here. Right. There's also going to be one where you've got the AI2 from the first row and the AI1 from the ith row, and the same more stuff over here, right? These would be two different things, two different elementary products that you get. However, these two are the same, and I want to argue that they'll be the same with opposite signs, and so they'll cancel out. And so this, in a previous video, I talked about these elementary products. I looked at when you've got them all listed here, whatever's in the first row, second row, third row, and you look at what columns they come from. I look at these columns, 1, 2, 3, 4 would be, going right down the diagonal. But if I swap two of them, like here, I've got, all this stuff is the same, but these two have just been swapped in their positions, then I claim that you change the sign that goes out in front, right? By putting the 4 in front of the 3, you've made one inversion. You've made one place where you've got a bigger number in front of a smaller number. But also putting the 2 on the other side of the 3 would create an inversion. So that's two inversions created. Two inversions doesn't change the sign. However, you've also swapped the 4 and the 2, creating a third inversion. So that's 3 inversions, and the sign changes. Right? On the other hand, if you swapped, so that was jumping over an odd number of rows. If I swap jumping over an even number of rows, so if I'm taking, let's say the 1 and the 4 and swapping them, so there's an even number of rows in between here. The thing is, the 4 coming out in front jumps over the 2 and the 3, creating 2 inversions. The 1 coming back to the other way jumps over the 2 and 3, creating those 2 inversions as well. Still, the 2 and the 2 is an even number of inversions, doesn't change the sign, but the 1 and the 4 are getting swapped as well, creating an odd number. A total of 5 inversions happen when you make this swap. There's 1, there's 2, there's 3, there's 4, there's 5, right? The 2 and the 3 are in the right order, but pretty much everything else is in the wrong order. So there's 5 total inversions there. That's an odd. So where this one would have no inversions with a plus sign in front, this would have an odd number inversion, so a minus sign in front. And every single elementary product that you choose will have something out of this first row and something out of the ith row, which will appear twice, because then you have to have the other thing out of the first row and the first thing out of the ith row. That you just swap these. The products will be the same, but the signs will be different, and you'll get a 0 out of it. Okay, so this right here is 0. I mean, it's kind of a powerful statement that if you use any row but use the cofactors of another row to multiply this thing out here, you're always going to get 0. It's only when you use the same row as the cofactors that you're using. So I'm using, here it's the first row and the first row cofactors, the first row and the first row cofactor. That gives you the determinant. Any other combination gives you 0. Okay. Anyway, the result is that adding a multiple of one row to another does not change the determinant. The determinant of this matrix is the same as the determinant of A. Okay. Now, I am going to stop at this point and make a new video.